Okay, let's evaluate some limits analytically. We'll start off with this one. Let's suppose we have the limit of, let's make this function x minus 1, and we'll take the limit as x goes to 5. Now, with this one right here, notice, well, first of all, let me just look at the graph of this function. Now, you won't always have to look at the graph, but notice that this is a square root function. It's been shifted over 1 unit to the right. And, you know, we're talking about what is the limit here at x equals 5. Well, you see there's nothing fishy going on. I mean, this is just a continuous curve here. We can just plug into this. See, so if we plug in, we get 5 minus 1. We get the square root of 4, which is 2. So, no worries. And most of the time, your default is going to be, the way you're thinking when you're evaluating the limit is, I'm just going to plug in. With this in mind, you have to be aware of what function you're dealing with. So let me take this same function, and I'm going to take the limit as x goes to 1. Okay, the same function, but the limit as x goes to 1. So this is the square root of x minus 1. Now, let's, once again, notice we've got this graph over here. If we're talking about as x goes to 1, dig what's going on here. Your right-hand limit exists, indeed, it does. Look, as you're approaching from the right, the limit is 0. So we could say, okay, the limit as x goes to 1 from the right, well, that's equal to the square root of 1 minus 1, which equals 0. However, if you think about the limit as x goes to 1 from the left, well, the graph doesn't even exist over there, right? That's not even in the domain. So we would say that does not exist. Now, in order for this limit to exist, the left-hand and the right-hand limit have to be the same. And on this one, the left-hand limit doesn't even exist. So we would say this limit does not exist. So you just have to be careful. When you're plugging in, be aware of the function that you're dealing with. Now, other than that, probably you can just plug in. Now, so let's look at some examples here. Let's suppose we've got the limit as x goes to 3 of, let's say, x squared minus 3x minus 4 over, let's say, x minus 4. Let's suppose we've got this particular limit to evaluate. Now, so remember, one of the properties of limits was we can just look at the limit of the top over the limit of the bottom as long as the limit of the bottom is not 0. So let's see if this works. In other words, what I'm going to do is just try plugging in and see if I get a number. So here I go. I've got 3 squared minus 3 times 3 minus 4. Okay, that's the top. Now on the bottom, I've got 3 minus 4. Okay, let's see. So far so good. There's not a 0 on the bottom, so that's nice. The bottom is going to be negative 1. Let's see what the top is. I've got 9 minus 9. Ooh, look at that. Minus 4. So it looks like that limit is 4. Okay, there. So just plugging in worked out nicely for us. Now let's try this same function, but now let me let the limit as x goes to 4. So I've got x squared minus 3x minus 4 over x minus 4. Now, if I plug this one in, look what I get. I get 4 squared minus 3 times 4 minus 4. And on the bottom, 4 minus 4. Ah, this kills it right here. Okay, let's see what happens up top, though. Let's see here. We've got 16 right here, minus 12, minus 4, and that is 0 over 0. Okay, now, so this limit right here, I said equals, but no, it doesn't. So I'm going to put not equals. Okay? Because I can't find this limit just by plugging in. Now, here's what happens. Whenever you try this plugging in thing and you get a 0 over 0, that's an indication that you have some work to do. So it doesn't tell you this limit doesn't exist. It tells you, okay, you got to do a little bit more work and then try plugging in. So here's what you do. In a situation like this where you have one polynomial over another one, like this, you try factoring and canceling. So you see if you can factor and cancel. Because the fact that you got 0 over 0 indicates that you probably have common factors. That's what you're thinking, right? You got 0 over 0. So in other words, I think there's an x minus 4 up here. But anyway, we try to factor it. So there's no factoring to do on the bottom. So let's see what we can do up top. This is going to be x, let's see here, minus 4 plus 1. Does that work? See, there's x squared, there's minus 4x plus 1x. Yeah, that works. Now, sure enough, look at this. These two things cancel. Those factors cancel. So here's the limit. The limit is x goes to 4 of x plus 1. Now we can plug in, and we get 4 plus 1 equals 5. And that's the limit. So notice, what we have to do sometimes in a situation like this is factor and cancel and then plug in. Originally, plugging in gave us 0 over 0. So what we do is we go to the next phase and say, okay, I'm going to have to do a little more work. So I'm going to factor and cancel. So this is one of the situations that you encounter where you have to simplify and then plug in. Now there are others. Let's look at this one. Let's suppose that we've got the limit, and let's suppose I've got 1 over x minus 1 over 2, something like this, and this is x minus 2, and I want to take the limit as x goes to 2. Okay, so let's suppose I've got this limit to evaluate. Now notice this is different than this one up here. This was one polynomial over another. This was a rational function, right? A ratio of polynomials. This one, it's a little bit different. So first of all, we try plugging in. So we got 1 over 2. Sorry about that. Okay. So we've got 1 over 2 minus 1 over 2 over 2 over 2. 2 minus 2. So that's 1/2 minus 1/2 over 0. Well, of course, that's 0 over 0. And that tells us, okay, we got a little more work to do. Now, up here, our job was to just factor. See, we factored the top over the bottom, and then we divided out the common factors. Not so easy to do here, so we take a different approach. What I do here on a problem like this where we have a complex fraction, see, we have numerator, denominator up top, and then we got in the numerator, and then we've got the denominator. So what I do is I multiply by the least common denominator. In other words, I look at these denominators, these extra denominators here, and I've got 2 and I've got x. I'm just going to multiply through by 2x because what I want to do is I want to get rid of this x. So I need to multiply by x. Well, I can't just multiply by x here. I've got to do it to all of it, here, here, and here. Likewise, I want to get rid of this 2, so I need to multiply by 2, but I can't just multiply by 2 here. I need to multiply by here, here, and here. So really, what I'm doing is I'm taking this limit as x goes to 2, and I'm doing something that's perfectly legal. I'm multiplying by 1. See? What I'm going to do is I'm going to multiply the top and the bottom by 2x. In other words, I'm multiplying the top and the bottom by the least common denominator, the 2x. See? That's fine. I can multiply by 1. It's just 2x over 2x. Now, if I distribute this 2x through, dig what I have now. I have this. I have the limit as x goes to 2 of, let's see here, 1 over x times 2x. Clean that up a little bit. 1 over x times 2x. See that? Minus 1 over 2 times 2x. And don't forget the bottom. Yeah, like that. See what I did? I just multiplied every term by 2x. Now the reason I did that is because now things start to cancel out and I get rid of these extra denominators. See? The x canceled here, the 2 canceled there. So now let's see what we have after we clean up everything. We've got the limit as x goes to 2. And up top now, look what we have. We have 2 minus x over 2x, x minus 2. Yeah, there we go. Now, notice I've got x minus 2 here and 2 minus x here. Those, you think, I wish that were x minus 2 and that were x minus 2, then I'd cancel them out. Well, look what you can do, though. You can view it this way. I've got the limit as x goes to 2, and I'll just factor out a negative up top. See, that's fine. That's a cool little move that we can do. See, just factor out a negative. Now look at this. X minus 2, x minus 2, and now look what I have. I have the limit as x goes to 2 of negative 1 over 2x. Well, now we've done that simplifying. Now let's try plugging in. We've got negative 1 over 2 times 2, which is negative 1/4, and that is our limit right there. After all that work, that limit is the negative 1/4, that's our limit. Okay, now, so look, we've got the rational function, factor and cancel, this complex fraction here, where we multiply the top and the bottom by the LCD. And now let's look at another one. A third type that might give us a little bit of vexation. Let's suppose that we've got the limit as, let's say x goes to 0 of, let's look at this. Let's suppose I've got 4 plus x minus the square, well, let's just do 2. 2 over x, something like this. Okay? Now, first thing I think about, okay, let me try to plug in here, and then if I can plug in and get out a good number, I'll just make sure my graph is okay, and then I'll call that a day. Well, look, first thing you notice is if you plug in this 0 in for x, you get a 0. And furthermore, if you plug in a 0 up here for x, you get the square root of 4, which is 2, minus 2, you get a 0 up top. So you have a situation where you have 0 over 0. So here's the trick for these. When you have a radical like this, the square root, you want to multiply by the conjugate. In other words, what I'm going to do, on the top and the bottom, I'm going to multiply by the square root of 4 plus x plus 2. I'm going to do that to the top and the bottom because that's the conjugate. See? Since it's minus 2, if I put a plus 2 there, that's the conjugate. Now, the reason I do that is because we have this situation where if you say a minus b times a plus b, if I multiply that out, notice I get a squared plus ab minus ab minus b squared. And notice this ab and this minus ab get rid of each other, and you just get a squared minus b squared. Now, imagine if that's square root. Let's suppose you've got the square root of a minus the square root of b times the square root of a plus the square root of b. Well, that's just going to be the first thing squared minus the second term squared, and you get a minus b. Notice, what I did was I got rid of the radical by multiplying by the conjugate. Well, I would like to get rid of that radical. So I'm going to multiply by the conjugate. Let's see what I'm going to have then. I've got the limit as x goes to 0. And let's see what's going to be left. Up top, I'm just going to have 4 plus x, the square root of that square, that's just 4 plus x, minus the second thing squared. There, look at that. A squared minus b squared. A squared, square the square root, you get this. Now, down on the bottom, let's see what's going to happen. We got x times this whole thing. See? Now, notice these 4's cancel out. And let's see where let's go down here where we can get a fresh start here. We've got the limit as x goes to 0 of x over x times the square root of 4 plus x plus 2. Now, here's the good thing. What happens now is this x cancels. And now we have the limit as x goes to 0 of 1 over the square root of 4 plus x plus 2. Now, now I can plug in, because look what happens. I got 1 over the square root of 4 plus 2. See? Because I just put a 0 in for x. See? There's what I have. And now that will give me 1 over 2 plus 2, which is 1 over 4. So that's how we deal with limits when we've got a radical like this. When we have something that looks like this, multiply by the conjugate. Yeah. Okay, so the three things. You've got a rational function where you can factor and cancel if you get 0 over 0. If you've got a complex fraction, you can multiply by the least common denominator. See? So here we go. The rational function, factor and cancel. The complex fraction, where you've got, numerator, denominator in the numerator, or it could be in the denominator too. You could have a numerator, denominators up here and down here. But you want to multiply by the LCD. And then we've got the other situation where you've got the radical, the square root. Multiply by the conjugate. And that's how we approach those particular types of problems.